Welcome. This is Dr. Michio Kaku, Professor of Theoretical Physics at the City College and the Graduate Center of the City University of New York. And this is Exploration. Every week on Exploration, we discuss the fascinating world of science and its impact on society. And today, leading off, well, we're going to answer some of the emails I get. Once again, I cannot possibly answer all the emails that I get, so instead of trying to answer each one, I'll try to answer them collectively on air. Sorry about that. Well, the first question that I've been getting in my emails is, when can I catch the next meteor shower? Well, in case you missed it, about 2 weeks ago, there was a fantastic meteor shower that quite a few people saw using the naked eye, binoculars, and even telescopes. You could literally see the shooting stars once every 30 seconds or 200 times in an hour. This is incredible. It's 2 to 3 times more spectacular than the average Perseid meteor shower. And first of all, the question is, what is a meteor shower? Why all this fuss about this meteor shower, and when's the next one going to occur? Well, believe it or not, the Earth moved through the tail of a comet 2 weeks ago. The comet is called the Swift-Tuttle Comet. It goes around the solar system once every 133 years, and it's like a cosmic litter bug. It literally sheds particles of ice, rock, and dust in its tail, and as the Earth goes through the tail, the debris burns up in the Earth's atmosphere, traveling at about 130,000 miles per hour, many times faster than a speeding bullet. And that causes the characteristic streak of light in the sky. So in other words, we are going through the tail of a comet. And in fact, you can see the remnants of the meteor shower as late as August 26. Now, why all the fuss this year about this meteor shower? This meteor shower, the one that you probably missed, is different because it is 2 to 3 times brighter and more frequent than the meteors in other meteor showers. What happened was the planet Jupiter interfered gravitationally with the motion of the tail of the comet. Usually when the Earth moves to the tail of a comet, it misses the center. This time, because of a small tug because of the gravity of Jupiter, it realigned the tail of the comet, so the Earth practically went right through the center of the tail. That's why you could see over 200 streaks of light. Now, why do they call it the Perseid meteor shower? Well, it's an optical illusion. It seems as if all these shooting stars are coming out of the constellation Perseus, named after the Greek god that slew Medusa. But that's an optical illusion caused by the fact that the Earth is simply moving through the tail of a comet that whizzed by the Earth decades to centuries ago. And then the next question is, well, some people say they missed the meteor shower. When's the next one? Well, first of all, the Perseid meteor shower comes by every year in summertime. So if you miss this spectacular one, next year there's going to be a smaller one in the month of, well, late July, early August. But there's also other meteor showers like the Leonid meteor shower. The Leonid meteor shower peaks around November 17, and it's called the Leonid meteor shower because the meteors seem to come from the constellation Leo the Lion, though, of course, that is an optical illusion. And so that's why they call it the Leonid meteor shower, and it peaks around the evening of November 17. And so, the next time around, check your local newspaper, find out when the moon goes down, because you get better viewing, and find out which direction you should face. For the Perseid meteor shower, you have to face northeast. For the Leonid meteor shower, you face east. And so, with this bit of advice, you too can watch a meteor shower. Now, do I need a telescope? And the answer is no. With the naked eye, you can see these little bits of rock whizzing across the entire sky. You don't even need binoculars for that. In fact, a telescope may get in the way. Telescopes are good for zooming in on a stationary tiny point. However, these things move right across the night sky. They are called shooting stars. And lastly, what is the difference between a falling star, a shooting star, a meteor, an asteroid, and a comet? Well, First of all, asteroids are pieces of a failed planet that never quite coalesce between Mars and Jupiter. Sometimes these asteroids cross the orbit of the Earth by accident. They burn up, leaving a streak of light. That streak of light is called a meteor. When the falling rock actually hits the ground, it's called a meteorite. And then, what is a comet? A comet is totally different from a meteor. A meteor will zip across the whole sky in about a second or so. Comets linger. They linger for weeks in the night sky, freaking people out. That's why people think that the coming of a comet foretells the death of a king. In fact, King Harold of England, he was defeated at the Battle of Hastings when his troops were frightened by Halley's Comet in the year 1066. Comets are gigantic. They come from way outside the solar system, in fact. They come from the Oort cloud and the Kuiper belt way out there in outer space. And because they are outside and they're so far away, they linger in the night sky, not just for seconds, but for weeks at a time. And if you've been watching the presidential debates between Hillary Clinton and Donald Trump, you know they've been slugging it out. However, did you notice that the concept of global warming very rarely is mentioned? And that's a shame, because last month went down as the hottest month ever recorded in the history of science. Last year went down as the hottest year ever recorded in the history of science. This decade will probably go down as the hottest decade ever recorded in the history of science. And have you noticed that around the world, we're seeing 100-year storms, 100-year floods, 100-year forest fires, 100-year catastrophes that should take place once every 100 years, but they seem to be taking place much more frequently. Yes, if you were to canvass scientists, they would say that with 95% confidence, not 100%, but with 95% confidence, the Earth is A, heating up, and B, it is human activity that is largely driving this whole process. Now, it was just announced a few days ago by the U.S. government that hurricane season this year could be more ferocious than in the past. In fact, it could be comparable to the years that brought us Hurricane Sandy and Hurricane Katrina. All the signs look like we're going to have a whopper. Now, of course, it's very hard to point your finger and say, ha, it's global warming that's causing this. Global warming is an average effect, and therefore it's very difficult to point to one particular incident and say, aha, that's due to global warming. But if you look at the trend, if you complete the dots, if you look at the averages, then it's unmistakable that things are, in fact, heating up and that human activity is largely driving it. And we tell that by looking at computer programs. For example, we can even run the computer programs backwards. And when we run the computer program backwards, we get the temperature and the climate of the previous years. And so in other words, our computer programs are so reliable that not only can they be run forward to predict more or less the weather of the future, they can also be run backwards, and you retrieve the data that is already in the record books, giving us confidence that we are on the right track. Also, speaking about outer space, have you ever noticed that the astronauts seem to be having a lot of fun being upside down in outer space? But the question is, why? Why can they go upside down like that in outer space? We even have commercials now, commercials selling you everything from candy to detergent with our astronauts floating upside down. And the question is it because there's no gravity in outer space? Wrong. There's plenty of gravity in outer space. In fact, the sun's gravity is so strong, it can whip Saturn and Jupiter around in their orbits billions of miles from the planet Earth. So why do we have weightlessness? Well, this was actually first figured out by Galileo. Galileo did that famous experiment showing that from the Leaning Tower of Pisa, if you drop a small pebble versus a cannonball, they each fall at the same rate. They fall at 32 feet per second squared. So in other words, that is the acceleration of gravity, and all objects from that height fall at the same rate. Therefore, if you're in an elevator and someone were to, God forbid, cut the cable, what would it be like inside the elevator? Inside the elevator, you would be weightless because the bottom of the elevator falls at the same rate as your body. And so is there gravity inside the elevator shaft? Sure. That's what's causing you to fall toward the ground. There's plenty of gravity there, but the floor is falling at the same rate you are, giving you the optical illusion that there's no gravity. In other words, in outer space, our astronauts are constantly falling. They don't feel the effect of the falling because the floor falls with them, giving them the illusion that they are weightless. This was first worked out mathematically by Isaac Newton himself. He drew a famous diagram where you have the globe of the Earth and you have him sitting on a mountaintop throwing a pebble. If you throw a pebble from a mountaintop, of course it lands toward the base of the pebble. But if you throw it faster and faster and faster, the pebble goes farther and farther and farther until it finally goes around the planet Earth and hits you in the back of your head. So in other words, the rock becomes weightless. It is constantly falling. But since everything else falls at the same rate, you don't notice it. So in other words, Isaac Newton's observation was the moon is falling. In fact, almost everything is falling, except you don't feel the effects of it because everything else falls with you. And so in an elevator, you have the optical illusion that you're weightless because the floor of the elevator falls at the same rate you do. So when our astronauts are up there in outer space, upside down, waving at us, they're falling. They're falling at 32 feet per second squared. But they don't hit the ground because the floor of the spaceship is also falling at 32 feet per second, and of course because the Earth is round. And speaking about outer space, scientists in San Francisco announced last week that 20 planets have been discovered orbiting other stars in outer space that look very similar to the planet Earth. They could be doppelgangers of the planet Earth. Not one, but 20 of them. First of all, the yeoman's work of detecting planets in outer space has been done by the Kepler satellite. So far, the Kepler satellite has identified almost 4,000 planets going around other stars in the Milky Way galaxy. Of them, most of them are Jupiter-sized, so we don't think that they support life as we know it. Jupiter, of course, has a gaseous surface. It's very cold, so we don't think that Jupiter has any life on it. However, now we find rocky planets similar to the Earth, similar to Mars and Venus, that are orbiting stars way out there in the Milky Way galaxy. And these planets are almost the same size of the Earth, and they're just right from the mother sun. By just right, I mean if they were too close, the oceans would boil. If they're too far, the oceans would freeze. They're just right from the sun in order to have sunshine and, in principle, liquid water. Now, we don't know if they have liquid water, but if they do, that is a game changer. Now, we don't know if they have liquid water, but if they do, that is a game changer because liquid water is the universal solvent. Is the amniotic fluid out of which the first DNA got off the ground. So if there are liquid oceans on these planets, it means that there's very likely the possibility of maybe microbial life getting off the ground. Now remember, these planets are very far away from us. They're 500 to 1,500 light years from the planet Earth. And a Saturn rocket going at full blast would take about 70,000 years. 70,000 years to reach just 4 light years from the planet Earth, let alone 500 light years from the planet Earth. Now, just because we've located a doppelganger, a planet that's only 10% larger than the planet Earth orbiting another star, it doesn't mean that we're going to be able to communicate with any aliens on that planet if there are any. Because a message would take 500 years to get there. So even though we pick up messages from that planet, let's say, in the near future, to respond to that message would take 500 years to get back to the planet and another 500 years to get back to Earth. So communication with one of these planets is basically out of the question. However, it does raise the possibility now of intelligent life in our own backyard, that is, the Milky Way galaxy. We now have a census of the Milky Way galaxy coming from the Kepler satellite. First of all, it turns out that almost every star we see in the heavens has some kind of planet going around it. That's right. Almost every single star seems to have a planet of some sort going around it. And of them, perhaps 1 in 20 have an Earth-like planet, depending upon how you define Earth-like. That means in our own backyard, in the Milky Way galaxy, there are probably 1 billion planets that look very much like the planet Earth. That is, they are just the right distance from the mother sun in order to have liquid oceans, and their gravity is comparable to that of the Earth because their size is roughly the same size as the planet Earth, and temperatures are mild. They're not super hot or super cold like on Mars or on Venus, but just right. Now, once we find a planet with all those characteristics, then, of course, there's a high likelihood that some kind of microbial life has gone off the ground in these planets. And then the last question that I always get is, how come they don't visit us? If there are 1 billion Earth-like planets in our neighborhood of the Milky Way galaxy, and if only the tiniest fraction of them have intelligent life on them, then how come they don't visit us? Well, as I say to my students, if you go into the forest, do you speak to the squirrels and the deer? Well, I don't, but maybe you do. Ever try to have an intelligent conversation with a squirrel or a deer? They just lose interest, and we lose interest too. We don't speak the same language. We don't have the same concerns. We are basically speaking on 2 different wavelengths, so to speak. And it's very difficult to have a conversation with them. And the same thing, perhaps if there are alien life out there, perhaps they have very little to gain by talking to us, because what do we have to offer them? If they can reach us across hundreds of light years, if they can reach us from these fantastic distances, that means they're probably a few hundred to a few thousand years more advanced than us. And if so, then what do we have to offer them? Well, not much. Also, a few months ago, we spoke on exploration about the possibility of a megastructure orbiting another star in the heavens. Now, if a Jupiter-like planet were to go in front of a star, starlight dims. In fact, that's how we know there is a Jupiter-sized planet out there. It dims by about a factor of 1%. However, scientists a few months ago found a star such that starlight dropped by 15 to 20%. Well, as you can imagine, all jaws hit the floor. Astronomers were then scurrying back to their drawing board wondering what could possibly cause sunlight to drop by a factor of 15 to 20% when even the planet Jupiter, the biggest planet in our solar system, would only drop the starlight emitted from our sun by 1%. Well, all sorts of cockamamie schemes came out. The one scheme that seemed to fit some of the data points is maybe a comet storm of some sort. But, well, to be very frank, comets are not very big, and you would have to have an awful lot of them to dampen the starlight by that much. However, there's another option out there that scientists don't want to admit, but yes, there is another option out there, and that is perhaps a Type 2 civilization is advanced enough to create a sphere to harvest all the sunlight from their mother sun, called a Dyson sphere. And a Dyson sphere could actually drop the sunlight down to 0. This means that, for example, if you are a planetary civilization and can harness all the energy of a planet, and then you move on to the next step beyond planetary energy, you encounter stellar energy. These are type 2 civilizations, perhaps a few thousand years ahead of us in technology, and they could play with stars. They just don't play with planets. They play with entire stars. And how do they harvest the energy from a star? You create a sphere called a Dyson sphere that would absorb all the energy from that star. It wouldn't waste any of the energy at all. All that sunlight turned into energy because of a sphere that goes around the star. Well, here's the idea. If there was a type 2 civilization out there, they could be capable of building a gigantic sphere around the star to harvest all the energy coming from that star. And if there was a sphere that was orbiting around the mother sun, it would be huge. It would be capable of casting a shadow, dropping starlight by 15 to 20%. Now, scientists, of course, are reluctant to believe in that because chances are it's a natural effect that is causing this anomaly. However, for lack of a better explanation, it's on the table. So that's right. We're not talking about little green men. We are talking about the possibility there's a type 2 civilization out there capable of harvesting a tremendous amount of the starlight from its mother sun. And speaking about mother suns and intelligent life, you probably saw it on the video. Every once in a while, someone photographs a UFO and puts it on the video. And the latest video I've seen actually looks quite realistic. It was a video taken by a passenger in an airplane with his cell phone. Looking at the window of his airplane, he saw 3 distinct bright lights. That's right, 3 dancing lights. And after a while, you could see the lights move. They would interchange position, weave in and out. And this went on for quite a few minutes. And then finally, they vanished off the screen. And you're left to ask yourself a question. What could possibly do that? I mean, here are 3 dancing lights moving neck and neck with an airplane traveling at, let's say, 500 miles per hour and effortlessly dancing and weaving among themselves. What could cause that? Well, let me be blunt about this. I don't know. However, there are explanations that you can make. For example, if you ever look outside the airplane window, you can see the reflection of lights inside your cabin reflected off the window. Let's say you get 3 tiny little flashlights, many flashlights, and you shine them off the window so the light would then reflect off the airplane window and then go into your eyeball. Then, by golly, it really does look like 3 flying saucers. Now, I'm not saying it's a hoax. I'm not saying that I know what's happening. All I'm saying is there are explanations, natural explanations, for what might be causing these UFOs. Are there UFOs out there built by aliens from outer space? I don't know. I'm not going to rule it out. It's definitely possible. But, as Carl Sagan once said, remarkable results require remarkable proof. And it's simply too easy these days. It's simply too easy to create hoaxes and forged evidence. So, I tell my students, the next time you are abducted by aliens from outer space, for God's sake, steal something. I don't care what it is. An alien chip, an alien paperweight, an alien paperclip. Steal anything so that you could say, aha, it's more than just hearsay. Here's the proof. The point I'm raising is very simple. Science is based on things that are testable, reproducible, and falsifiable. So in other words, it's more than simply a question of, well, I saw something last night in my backyard. It was blinking lights. Maybe it was a flying saucer. Maybe, maybe not. So in other words, there has to be more than simply hearsay evidence. Because even though you could be absolutely correct, even though a flying saucer did land in your backyard, there's nothing to substantiate it because, of course, there are also hordes of hoaxers out there. For example, look at the Bigfoot phenomenon. A few years ago, a family admitted that their dear father, who had just passed away, had in his basement all sorts of contraptions to create fake footprints of Bigfoot. In fact, many of the footprints of Bigfoot were manufactured in the basement of this person's house. And the children were flabbergasted. The children had no idea that their father was fabricating the legend of Bigfoot by creating realistic but fake imprints of footprints. In other words, they knew that the father was a comic, that he was fond of making practical jokes. However, they had no idea that he almost single-handedly created most of the Bigfoot legends around that community. So in other words, science is based on things that are testable, reproducible, and falsifiable. That is the foundation for all of science. And that's it for the first part of exploration. In the second part of exploration, we're going to talk about one of the hottest areas in physics today, and that is the question of time travel. Is it really possible that we can bend time into a pretzel? Like in the science fiction movies, they go back into the past, maybe on a DeLorean like in Back to the Future? With us today is a physicist, Dr. Richard Gott of Princeton University, where Einstein used to teach. And we're going to talk about his proposal to build a time machine. Once again, if you want a copy of today's program, call the Pacifica Program Service at 1-800-735-0230. Stay tuned now as we talk about time travel. Welcome. Once again, this is Dr. Michio Kaku, Professor of Theoretical Physics at the City College and the Graduate Center of the City University of New York. And this is the second half of Exploration. In this segment, we're going to be talking about the cutting edge of theoretical physics, my field, specifically black holes and even the question of time travel. Now, black holes, of course, are common in science fiction and also on science documentaries, but there's a lot we don't know about Einstein's equations. Einstein's equations do predict that a dying star could eventually become so massive that even light itself cannot escape. And Einstein's equations also predict the possibility of time travel, that is, going backwards in time. Very rare, but with us today to talk about these things is Professor Richard Gott of Princeton University, who has his own version of what a time machine will look like. And doesn't look like anything you've seen in the Hollywood movies. And so first, once again, black holes are a solution of Einstein's equations like time machines, and yet we're still left with a very puzzling question. If all that matter comes tumbling into a black hole, then where does it go? Well, to be blunt about it, we physicists don't really know. There's a controversy among physicists as to what happens. Some people think that stars are simply crushed into nothingness and, well, that's it. Period. End of story. The black hole has just had lunch. Other people say, well, not so fast. Perhaps black holes can be gateways to another universe. And then the question is, well, what lies on the other end of that universe? And again, we're now entering the realm of science fiction because Einstein's equations break down. They break down at the two most interesting points in space and time. First, the center of a black hole. Einstein's equations are useless at that point. Einstein's equations do predict that black holes might be used as time machines or gateways to other universes, but these equations are unreliable because the gravitational force at the center of a black hole becomes infinite, and that's nonsense. It just means that Einstein's equations are incomplete. The second place where Einstein's equations break down is the center of the Big Bang. Another very interesting place. We simply don't know what happened before the Big Bang. Well, now we have something called string theory, which is what I do for a living. That's my day job. And in principle, we might be able to answer these questions of what happens if you go through a black hole or what happens if you go before the Big Bang. And string theory seems to indicate that if our universe is a bubble of some sort, then there are perhaps other bubble universes out there that are also expanding. And if these bubble universes collide, or if these bubble universes peel off a baby universe, then perhaps that's the Big Bang. So it's fair game now to ask what happened before the Big Bang. But what about time travel? Well, again, we have to rely on string theory. String theory is not advanced enough to answer that question. But if time is a river, as Einstein said, then that leaves open the possibility that the river of time could have whirlpools. And if the river of time has whirlpools, these are called closed time-like loops, and it allows you to leave, let's say, your office, and come back before you left. In other words, you might be able to come back yesterday. Now, this, of course, is all nonsense, you might say to yourself, but hey, these are logical conclusions of Einstein's equations and perhaps may even be allowed by string theory. So our next guest is Dr. Richard Gott of Princeton talking about time travel. And now I'd like to introduce our very special guest today. Once again, we have with us Professor J. Richard Gott III. He's a professor at Princeton University, and he's the author of a book called Time Travel in Einstein's Universe: The Physical Possibilities of Travel Through Time. Now, just remember that we're not talking about some inventor in a laboratory in his basement creating a time machine by which you can erase certain rather embarrassing events in your history. We are, in fact, talking about hard physics. We're talking about perhaps one day a civilization much more advanced than ours, or perhaps maybe even our descendants thousands of years from now, may have the ability to manipulate the energy of a star, in which case they may be able to create a time machine capable of changing the past. And so the question is time travel possible, given the fact that there are all sorts of horrible paradoxes you can get if you go backwards in time, for example, and shoot your parents before you're born? So once again today, our guest is Professor J. Richard Gott III, a professor at Princeton University, and we are talking about time machines and time travel. The first question for you, Professor Gott, is how did you first get interested in physics?
Well, I got interested in astronomy when I was about 8 years old. I belonged to a stargazer group that was organized by our Junior Astronomical Society, and so I had a telescope, and astronomy was a hobby of mine in high school. And when I became interested in physics in high school and so forth, I later decided to take my physics and work on astrophysics because that had always been a hobby and of particular interest to me.
And was there anything about the romance of the stars? Anything about, for example, looking for intelligent life in outer space or wondering where the universe came from? Was there anything specific about astronomy that fascinated you?
Well, I was particularly interested in the Big Bang theory. At that time, this was a bit before Penzias and Wilson had discovered the cosmic microwave background radiation. So I was always a fan of the Big Bang theory versus as opposed to the steady state theory.
Okay. And I understand today you're affiliated with the Intel Science Talent Search, or formerly known as the Westinghouse Science Talent Search. So tell us a little bit about your experience judging high school kids.
Well, for many years I was the chairman of the judges for the first Westinghouse, and then it's now sponsored by Intel, the Intel Science Talent Search. And this is a wonderful science competition. It's the oldest and most prestigious competition for high school students in science in the country. And 5 of its winners have gone on to win Nobel Prizes. So it's a wonderful contest, and it asks you to do a piece of real research and submit your research just like you would write a research paper and so forth. So unlike a test of some sort, it's really you just try research, and we look at your research. So it's kind of like if you were a baseball camp, you could test people out by seeing how fast they ran down to first base. That would give you some idea of how they might play baseball. But a baseball scout would tell you that it's really, if you're scouting for the major leagues, you really want to see people actually play baseball. So this gives students a chance to do real research projects, which are fun. And many people that enter this contest, they fall in love with doing research and do it for the rest of their lives. And many of the winners of this contest have gone on to wonderful careers in science. So I would encourage people to apply for it. 40 winners come to Washington each year, and they give out very large college scholarships, and it's a very exciting thing.
Okay, now let's talk about time travel in particular. There's a movie hitting the silver screen right now called Terminator 3, where killer robots from the future come back to harass us in the past. So what started your romance with time machines? Because in the area of physics, most physicists tend to, at least in the old days, scoff at the whole notion of going backwards in time.
Well, I got interested in time travel by exploring some solutions to Einstein's equations. Einstein developed his theory of general relativity, which is his theory of curved space-time to explain gravity. And we take this theory very seriously because when he finally solved the equations for this in 1915, they made predictions about light bending or as it would pass near the sun, and these were checked experimentally, and Einstein was found to be right and Newton was found to be wrong. So since then, people have been interested in exploring exact solutions to Einstein's equations, and you've heard of probably the most famous one is the black hole solution. That's an exact solution to Einstein's equations. So we take black holes seriously, even though they're quite extraordinary objects, because they do solve Einstein's equations of gravity. So I got interested in cosmic strings. These are theoretical objects that are dense threads of energy left over after the Big Bang that are predicted in about half the theories of unified particle physics in the early universe. We haven't found them yet, but we are searching for them. And I found an exact solution for one cosmic string, what the geometry around one cosmic string would look like. And William Hiscock found the same solution independently of me, so we're given joint credit for this solution to Einstein's equations. And then later, I investigated two moving cosmic strings, what an exact solution would look like if two strings were to pass each other. And I indeed found an exact solution for that geometry. And it turned out that if the strings were moving fast enough but still slower than the speed of light, that this was a solution that would allow you to circle around the cosmic strings and arrive back home before you started. So it would allow time travel to the past. And there have been a number of general relativity solutions like this. The first one was found by famous mathematician Kurt Gödel in 1949. It's a rotating universe that we don't live in that kind of universe, but it's an interesting solution to the equations that allows time travel to the past. And if there's one solution like that, there could be others. And then Kip Thorne and his associates found wormhole solutions that allowed time travel to the past. So it's extremely interesting that these equations of Einstein's of general relativity themselves, and this is our best theory of gravity at the time, seem to allow solutions that allow time travel to the past. So I got interested in it just from trying to understand Einstein's equations with objects that we were interested in.
Okay, now let's talk about the movies. Everyone likes the movies, and people have seen a lot of movies where we have black holes that are rotating very rapidly.
Right.
And according to mathematician Roy Kerr in 1963, he did find a solution of Einstein's equations where if you pass through the ring, not a point, but a ring that's spinning very rapidly, you would wind up on a parallel universe, perhaps even in a distant point in time. So could you elaborate about what happens if you, heaven forbid, fall through a black hole and make it, quote, to the other side, unquote?
Well, this was an unperturbed black hole. It's the solution to Einstein's equations, and this is one that's left alone completely, and you ignore the effects of Hawking radiation, which we can mention later. But this first solution for a rotating black hole showed that if you traveled inside the black hole, instead of a singular point in the center, you would find, as you said, a ring singularity. If you passed through the ring, you could navigate your spaceship in such a way that you could travel back in time. And then after leaving this region, you could go and pop out into another universe, sort of like getting on an elevator at a store and going up to the first, going from the first floor to the second, and you could get out on the second floor universe. Then later you could go out and go up to a third floor universe and so forth. But there was no getting back to the first floor. Once you went in the rotating black hole, it was not possible to come back outside and brag to your friends about your adventures. But quite interestingly, there was a region of time travel that was trapped inside the rotating black hole in Kerr's solution.
Okay, now let's say you go through the black hole and you're not crushed by gravity because it's, gravity is spread out a little bit throughout the ring. However, there are some naysayers who say, wait a minute, let's not go so fast. And you mentioned that the black hole was not perturbed. So could you tell us a little bit about some of the naysayers who say that maybe you can't make it quite all the way through that black hole?
Well, the trouble is that when you pass inside this black hole and you pass into the region of time travel, if you're looking back outside, you're seeing the history of the external universe as you're passing outside. And in Mr. Kerr's solution, as you passed into the region of time travel, you would be able to see the entire future history of the universe pass before your eyes. Now, you might say, well, this is a good thing, very interesting for historians. You get to see the whole future history of the universe in a finite amount of time. But the trouble is those photons coming in would be infinitely blue shifted and become, instead of visible photons, they would become ultraviolet and gamma ray photons. So these could kill you. You have to pass them on your way into the region of time travel. Other effects need to be considered, too, like the fact that the black hole may evaporate, would it be expected to evaporate from Hawking radiation, which cuts off your view of the very late history of the universe, but also induces other effects, quantum effects on the inside of the black hole. So the situation is that some people have explored this situation, Mr. Burko, for one, Amos Ori, and they have found that traveling to the region of time travel, you would probably pass a singularity. The curvature of space-time would become infinite. However, it takes a very brief amount of time for this to occur. So the singularity may be weak in the sense that it may not tear your body completely apart. And also quantum effects would be expected to knock out any infinities in the solution. So the trouble is that we don't really know exactly what happens to you when you go inside a rotating black hole, and we may need a theory of quantum gravity to explain this. We know how gravity behaves on macroscopic, ordinary scales. Einstein's theory gives us a wonderful and very well-checked theory of that, but we don't know how gravity behaves on microscopic scales, and to understand what would really happen going into a black hole, we may need to know that.
Okay, well, we have had on this radio show several people who work in superstring theory, like I do, and we do look at these things. However, the theory is not very well developed yet. So let's ask a hypothetical question. Let's say you are an advanced civilization, like we see in the movies, an advanced civilization that can move planets and move stars. I mean, really powerful technology you're having here now.
Yeah.
With that kind of technology, do you think that someone could go through the ring to perhaps a parallel universe, or perhaps in time, or it's just simply not known in terms of what we know about quantum gravity? Or do most people think, bah, humbug, you just can't do it?
Well, I think that if you were using my cosmic strings, what a super civilization would try to do is find a loop of cosmic strings. Cosmic strings either are infinite, they have no end, so either they're infinite if we found them. They're either infinite or they come in loops. So you can think of spaghetti or SpaghettiOs. So find one of the SpaghettiOs, one of the loops, manipulate it so that it collapses by a large factor, and you could arrange it with your massive spaceship flying around it so that the two sides of the string would pass each other at the speed required to make a time machine. But I was able to show in that case that this would also be in grave danger of forming a black hole. In fact, it would likely form a black hole. So the regions of time travel would likely be trapped inside, just as we've talked about in the rotating black hole case. So I think one thing to emphasize is that these are projects that really, this loop would weigh half the mass of our own galaxy. So we're talking about projects that really only a super civilization could attempt. But as you say, we're interested in finding out whether a civilization with arbitrarily large powers, but still operating under the laws of physics, could do it. And I think probably until we really get a theory of quantum gravity, we can't say for sure whether they would succeed or not.
Okay, now let's talk about the wormhole, because on Star Trek, they simply zap through wormholes to the other side of the galaxy. Now, if you had a black hole, there is a problem there, and that is it's a one-way ticket. It's basically a roach motel. You go in and you never check out again. It's a one-way trip. However, these wormholes that we see on Star Trek are transversible. You go back and forth, back and forth. It's like taking a Sunday drive right through a wormhole. So tell us a little bit about wormholes and whether or not they're practical.
Well, the wormhole idea got started when Carl Sagan, who was writing this book, Contact, which later became a famous movie, he wanted to use a wormhole to get Jodie Foster from one part of the galaxy to another. And so he called up his friend Kip Thorne and said, listen, I'd like to get the physics right here. What about the physics of wormholes? So Kip Thorne and his associates investigated this, and they found out that in order to transverse it back and forth, you had to prop it open with some what we call negative energy density stuff. This is stuff that weighs less than zero. In other words, you'd have to add mass to this to get back to zero. It's stuff that weighs less than zero. Well, that's very strange stuff, but you might say, well, that's strange. You wouldn't expect to find that. But curiously, we do know of a quantum mechanical effect, the Casimir effect, which is one where if you take two parallel metal conducting plates and you put them very close together, the quantum vacuum state in between the two plates actually acquires a negative energy density. It weighs less than zero. So Kip Thorne was proposing, and similar effects occur in connected with Hawking radiation and black holes and so forth. So we know of quantum effects that can induce negative energy density states. So what Kip Thorne proposed to do was to cover the mouth of each wormhole with a conducting plate and put them close to each other in the wormhole tunnel, 10 to the minus 10 centimeters apart, so that they introduced a large negative energy density. And then you could traverse by opening trapdoors in these metal plates. You could traverse the wormhole and not be killed. So again, the engineering effects of this were enormous. The wormhole he was talking about involved 200 million solar masses, 200 million times the mass of the sun. So, but again, he was interested to know whether these things were possible in principle at all under the laws of general relativity.
Okay, well, let's say you want to build one of these things, okay? People talk about these things. Paul Davies, who we actually had on the radio show a few years ago, even wrote a book about how to build a time machine, okay?
Sure.
Now, again, one of the problems is you have to get negative energy if you go the route of the wormhole. And then the question is, well, how do you get negative energy in large quantities? The Casimir effect is very tiny. It takes laboratory instruments, very delicate instruments, to measure this effect. However, we want to just rip space and time apart and change the topology of the universe. So if you were, once again, a very advanced civilization, how could you possibly assemble large quantities of negative energy to open up a wormhole?
Well, the mechanism that's being used is to bring the plates very close together. The plates are pulling you toward each other. This effect has been measured in the lab, And if you let the plates go very close to each other, you can get a very large amount of negative energy density. We have to engineer this so that the plates can go. In Kip Thorne's case, he was having them 10 to the 10th centimeters, 10 to the minus 10 centimeters apart. So that's the mechanism that's used. How do you get the wormhole in the first place? The idea here was that space-time on very small scales, 10 to the minus 33 centimeters, microscopic scales, may be sponge-like. The quantum fluctuations might be causing little microscopic wormholes to be forming all the time. And so the idea would be to find one of those and somehow enlarge it. This was Thorne's proposal, and make it large enough so, and then you could keep propping it open with this negative energy density stuff. So, no doubt, it's an extraordinarily difficult feat, but we're interested to know whether it's possible in principle.
Okay, well, there's even a television commercial now I was watching talking about building a wormhole to deliver products to the customers. So the idea of wormholes is out there. However, the advertisement stumbles on this whole question of, well, how do you energize this thing with negative energy? So you mentioned the Casimir effect. Where else in the universe can we find negative energy? It's a very exotic kind of thing. It's not the kind of thing we see in the laboratory. Where else in the universe can we find negative energy?
Well, black holes is one location. When Stephen Hawking was working on black holes, one of the things he proved was that if once you formed a black hole, it would only get bigger. Its horizon, as it were, would only get bigger. And so as it gobbled more and more material, in fact, he proved a theorem that if energy density was always positive, the black hole, if you just add energy density to it, the black hole would always get bigger. But then people started to think about what would happen to a black hole with quantum effects, and Stephen Hawking showed that black holes actually evaporate. And so over time, there's a quantum vacuum effect in the empty space around the black hole that you have vacuum fluctuations that cause particles to be emitted from the black hole and then also cause the black hole to lose energy. And so if you look at the quantum vacuum state that exists around the black hole, which Stephen Hawking found, it has a slight negative energy density which steals energy from the black hole and causes it to evaporate. And so that's an example of a naturally occurring phenomena that we expect is occurring every day.
Now, Paul Davies, in his book on how to build a time machine, stumbles over this very same question, and he mumbles that, well, maybe we can build banks of laser beams. Lasers can have positive and negative, what are called squeeze states, and he doesn't explain how to do it. And this is, of course, the key question. What is the gasoline? What is the energy that drives your machine? And he mumbles and says, well, maybe one day we'll have huge banks of lasers that we could fire into our chamber to prop open the mouth of a wormhole. Are you impressed by that book?
Well, I probably wouldn't use lasers. I mean, I still think the Casimir effect that Thorne talked about is the most promising proposal to get the negative energy density state.
Well, unfortunately, that's it for Exploration. Once again, our special guest was Professor Richard Gott, Professor of Physics at Princeton University, who has his own version of a time machine. And once again, this is Dr. Michio Kaku, Professor of Theoretical Physics at the City College and the Graduate Center of the City University of New York, inviting you to join us every week when we discuss science and its impact on society. Good day.